So now moving on with accuracy and precision. And just important to know is if we go into accuracy and precision, first of all, when we carry out labs at school, we're not creating something brand new. We're repeating something that's been proven over and over again. They're just very successful labs and they're very consistent labs. So what we're really teaching you here in the process in our labs is actually laboratory technique. We want you to develop those skills so you're actually again learning the proper technique. But in the process of doing so, we need some way to be able to measure what we're actually doing. So that's where we introduce absolute and relative error. So absolute error again is just the observed minus the accepted. Like we saw in class, it just gives you a number. And so it's helpful if you're doing the actual research yourself and doing the statistics behind it. But as for someone else on the outside looking in, that individual number doesn't always make sense. So what we'll do is divide by the accepted value once again, multiply by 100, we change it to percent error, also called relative error. So why do we need this? Why do we have to? Why are we talking about this accuracy and precision? Accuracy, again, by definition, is just how accurate you are with your measurements, whereas precision, you're talking about consistency. So we know already when our first lab, I brought up the aspect of uncertainty with our measurements, and just because we don't know with certain tools, we have to make that educated guess, and that's really where letter B comes into play, because that's our human error as we try to make these proper measurements. There are some other things though that come into play and produce possible error, and that is tolerance, and that's good, again, just about probably the more looking at the quality of the equipment, whereas malfunction of the equipment also ties in with that. Conditions of the room, but again, like I said, the main one there is uncertainty. Human error, and that is really the main reason why we have to give some uncertainty to our measurements, to give us some cushion, just knowing that we're not perfect. So good examples of accuracy and precision. I have a dartboard here, and we see the first one. We can say they're somewhat accurate, but they're not precise. They're not consistent. The second one, we can say, yeah, they are definitely accurate or precise, but they're not accurate. And then the third one, we say they're definitely accurate and definitely precise. Whereas the last one, they're neither or. And so, so in that one situation, we see accuracy once again is dealing with actually how accurate you are or correct you are, or precision is talking about just how consistent you are with each one of your measurements. Now we talk about we brought in this accuracy and precision, we brought in absolute and relative error. For the equations for absolute and relative error, absolute error is an absolute value, and all it is the observed, and that's your measurement, minus the accepted, and that's the true value. That's the universally accepted value. You'll never have to memorize those accepted values. I always provide them for you. But we want to take it a step further, and so what we'll do is we'll take the absolute error, which is your score, divided by the accepted value and multiply by 100. Another way you can write this out is E subscript R representing relative error, also called percent error, and it's your EA divided by A times 100. So we'll say a student measures the length of an object, and again, the student measured it out to be 7.45 centimeters. The actual length of this object is 8.00 centimeters. 0.00 centimeters. So as we take the observed minus the accepted, it's the 7.45 minus the 8, and we take its absolute value. So it really doesn't matter if you do A minus O or O minus A, because it's always the absolute value. What we see here now is we're dealing with this very, very important. We're dealing with addition and subtraction rule. So we're subtracting these values. So with the addition and subtraction rule, we know for sig figs, it's not looking at the least number of sig figs, it's looking at the number with the least number of digits to the right of a decimal. Well, 7.45 only has 2 digits to the right of a decimal, therefore my answer is limited to only 2 different digits to the right of a decimal, and that would be 0.55. Now we're going to go on and continue on. That's your score, 0.55. Again, it really doesn't have, you don't know is that good or is it bad. You would know more if you were the one actually doing research. So what we're going to do is we're going to change it to percent error. a relative error. So we're going to take your score, 0.55, and divide it by the total, which was the accepted value, 8.000. Now, your score has 2 sig figs, 8.000 has 4 sig figs. Now we're doing division, so we're looking for the measurement with least number of sig figs. That means it's 2. That means your answer, you're going to have 2. Your percent will have 2 sig figs. And the percent ends up being 6.9% error. So if we look at an example of this, I gave you aluminum block, and we did this in class, and we know aluminum is rectangles, length times width times height. We know we're going after, I want you to solve the density, and then we're going to carry out substitution. So it's going to be mass divided by length times width times height. So I gave you the mass at 53.52, I gave you the length at 4.95, the height at 1.25, and the width at 2.95. Each of my measurements, length, width, and height, all have 3 sig figs. My mass has 4 sig figs. Therefore, my answer will be limited to 3 sig figs. But all I'm going to do is take my 53.62, divide by 4.95, divide by 1.25, divide by 2.95 equals. And so this process gives me 2.94 grams per centimeters cubed. Now, if you look down the next segment, I give you what is the accepted value of the density of aluminum, and that is 2.70 grams per mil. I want you to calculate the absolute and the relative error. Well, the absolute is easy. It's either 2.94 minus 2.7 or vice versa. It doesn't matter because it's the absolute value. Both of them have 2 digits to the right decimal. Therefore, my absolute value will have 2 digits to the right decimal, and it is 0.24 grams per mil, or grams per centimeters cubed. Now, I want to now change this to a percent, because 0.24 really doesn't have a whole lot of meaning for me. So we take it, we're going to divide by the accepted value, which is 2.70. Now 2.70 has 3 sig figs, 0.24 has 2 sig figs, therefore your percent will only have 2 sig figs, and that is, and that answer is 8.9%. The next one is I give you a cylinder, and we know that with the cylinder the volume equals pi r squared h. You then have the density given to you, and you have the height. So in that situation, with density and height, half your diameter, is your radius, and so 2 divided by 2 is 1. So it's going to be really, really easy. We're actually going after density. Density equals mass over volume. In place of volume, I'm going to substitute it with my pi r squared h. And then all I have to do is enter my mass at 65.32 divided by pi divided by my height, which is 2.67. I don't even have to worry about the radius because it's 1. 1 squared is still 1. So my answer here in this situation, all my height and my diameter both have 3 sig figs. Mass has 4 sig figs. Therefore, my density can only have 3 sig figs, and the answer is 7.79 grams per centimeters cubed. Now, the accepted value for this steel is 7.87 grams per centimeters cubed. Both of them have 2 digits to the right decimal. So when I go after absolute value, my absolute value will have 2 digits to the right decimal, and its value ends up being 0.08 grams per centimeters cubed. But now I'm going to go on to determine my relative or percent error. So now I'm going to take my 0.08 divided by my accepted value, 7.87. My 0.08 as an individual number by itself only has 1 sig fig. My 7.87 has 3. Therefore, my answer can only have 1 sig fig, and we're now percent error is reduced down to only 1%. The next example, we calculate the density of a sphere. Now, the sphere, I give you the mass of the sphere, and I give you the diameter of the sphere. And we know the volume of the sphere is 4/3 pi r cubed. We're going after density. We're going to substitute in place of volume 4/3 pi r cubed. We've done this over and over again. We will get rid of the fraction. We multiply through by its reciprocal. But now the nice thing about this situation, we don't have to rearrange it. It's already set up to solve for density. We just have to plug in our mass, and then half of our diameter is 1.45. So 3 times 99.495 divided by 4 divided by pi divided by 1.45 cubed equals, my diameter has 3 sig figs, and my mass has 4. Therefore, my density can only have 3 sig figs. And the answer comes up at this one at 7.83 grams per centimeters cubed. Again, this is steel, so the accepted density of steel is 7.87. Both of them have 2 digits to the right decimal, therefore my absolute error will have 2 digits to the right decimal. The units stay intact in this, they are not canceling out, but my absolute error is 0.04. So it only has 1 sig fig as individual number. So to divide, my percent can only have 1 sig config. So I divide that by 0.04, but my accepted value is 7.87, and then my percent error, which is 0.5%, which is actually really good. So elements. So elements are a substance in which all the atoms have the same number of protons in the nucleus, and J.J. Berzelius, a Swedish chemist, generally given credit for creating the modern symbols of the elements. No, J.J. Berzelius, one of the scientists. We're getting now into some theory here, so scientists, make sure you know them. Don't have to worry about dates, just know they're scientists and what they helped, or what they did. So we know the atomic number, the number of protons. There are approximately 118 elements that we know we have today, 82 of which are naturally occurring elements. 43 and 61 are up. Generally, the ones higher up are going to be naturally occurring. The ones lower down are going to be man-made. But 43 and 61, right in the mix of things, are actually man-made. 93 and beyond are man-made transuranium elements. And the names and symbols, when we're getting into that, I'm going to give you some quizzes. But the names and symbols working with is very, very important. That some of them you'll see actually have the symbol represents taken directly from their name, or the English spelling of their name. So carbon is capital C, calcium capital C lowercase a, chlorine capital C lowercase l. It is important to understand that when you have an element that has two letters for the symbol, the first one's uppercase, the second one is always lowercase. Then we move on to some that are man-made, but they haven't quite been named yet, so they have their place on the periodic table, like 104, and it's the symbol for 104 is UNQ, which is unil quadium. So un 1 nil 0 quadium representing 4, so 104. So again, it's a slide from Chang. The elements in a substance cannot be separated into simpler substances by chemical means. There are about 118 elements have been identified. 82 elements are naturally occurring on Earth: gold, aluminum, lead, oxygen, carbon. Examples of those. 36 elements have been created by scientists, such as technetium, americium, seaborgium. So again, all of these, there are a number of those. We don't really get down into those and deal with them, but again, it's worthwhile being familiar with them. So we now move on to, I want to talk about elements that don't actually, or have a symbol doesn't come from the English spelling. Well, where does it come from? Many of them come from the Latin. We don't expect you to know Latin. I'm just going to tell it to you, but you are not expected to know this for the test. Sodium is Na. And so Na is not anywhere within sodium. So where they get it? Well, it's from the Latin, which is natrium. Gold, Au, from aurorum. Silver, Ag, from argentium. Potassium, K, from calcium. Lead, Pb, from plumbum. And we know we talk about this in class as a root for plumbing. Antimony, Sb, sibonite. Iron, Fe, ferrum. Tungsten is a W. This is actually from German background, root, and this is wolfram. We have tin, Sn, and that is stannum. Copper, Cu, that's cuprum, and mercury, Hg, which is hydrogyrum. Hydro meaning liquid, and gyrum, metal, so liquid metal. Some things you need to know about the elements just in general. 3 states of matter. We're dealing with our solids, liquids, and gases. I'll put a lowercase s in parentheses or an L or a gas representing what state we find it in. Mixture is 2 or more elements of a compound physically joined together. Example here for a mixture would be an alloy: brass, copper, and zinc. Bronze is copper and tin. Both those were actually brought up in the actual video we watched, Hunting the Elements. The compound has 2 or more elements that are chemically bonded one to another, such as water, H2O. And then elements cannot be decomposed into simpler substances by chemical or physical means, excluding nuclear processes. Elements on the periodic table. So as we go down vertical columns, we call them groups or families. As we move across a row, we call them periods. There are some groups and families I want you to know. So alkali metals are group 1, except for hydrogen. Alkali metals are group 2. Your halogens are group 17. Your noble gases are group 18. And we can break the periodic table down into 3 general groups. We have metals on the left-hand side, and you have non-metals on the right-hand side of the staircase. Elements touching the staircase are metalloids, or also we call them semi-metals. All of them except aluminum. Aluminum touches the staircase, but it's not a semi-metal. Most elements are solid, and we'll know that if we look on the periodic table. Elements on the periodic table that are black are solid, red are a gas, and blue are a liquid, and that's at room temperature. So we see like sulfur, carbon, sodium, they're all solids at room temperature. Some are gases, and a few of them are liquids at room temperature. Those examples, only 2 that are actually liquids at room temperature, and that's bromine and mercury. And then we have the idea of the periodic table, again moving across the row. We call it period, up and down, we call it group or family. The first group are alkali metals, second group over there are your alkaline earth metals, group 17 are halogens, group 18 are your noble gases.